Hello future Ps, this is Wasim Asgar. I'm a licensed professional engineer in US and Canada. I've authored several books on the topic of FE electrical and computer exam preparation, as well as a P power exam preparation. I run popular programs for FE electrical and computer exam prep, as well as a P power exam prep. In this video, I'm going to go over a question that I received from one of my students during the live training, and this question relates to ground resistance testing. Ground resistance testing is one of the very first few topics that you will come across when you start your P power exam preparation. It is part of section number 1, which is general power engineering, and subsection A, which is measurement and instrumentation. General power engineering, along with section number 4, is one of the heavy hitters on the exam, and it is very important that you take good care of it, because otherwise you're going to struggle if you don't do well on these two big sections. The interesting thing about ground resistance testing is that there are quite a few equations that are provided to you in the reference handbook, but you will find that in this particular question that the student is asking, it's fairly simple, straightforward, but if you don't understand the concept fully, chances are that you're going to miss points on relatively easy concepts. And the PE power exam is anything but easy. Even the straightforward concepts can be so convoluted that sometimes students struggle in figuring out how to even get started. The approach that I take in my PE power exam preparation program is pretty simple, straightforward. I use a first principle based approach where I don't assume that the student is starting with a lot of prerequisite knowledge. We take baby steps in the program in order to create a solid foundation upon which the skyscraper of PE power exam preparation is erected. If you want to learn more about my FE electrical and P power exam preparation programs, please visit my website www.studyforfe.com. And if you're new to this channel, consider subscribing to it, because on a weekly basis, I'm publishing interesting content related to exam preparation for both FE electrical and P power. I also address topics related to electrical engineering, career development, and much more. So without further ado, let's dive into the content. This is an interesting question. So this is basically the question that I was asked. This is the question from the student, included the screenshot from the quiz problem. Hi, Wasim, am I misunderstanding this question? Thanks. And the question is saying, correctly describe the impact of electrode dimension on grounding resistance. Okay, so his solution, he selected that resistance increases with the increase in electrode length. And the equation that he sort of included to sort of support his argument is that resistance R is equal to rho resistivity, which consider it as a constant, it's a material specific property, times L, right? Divided by A, correct? So he ended up selecting this. Resistance increases with the increase in electrode length. Since length is appearing in the numerator, if that increases, then resistance is going to increase, right? But the answer, as we all know, is different. Resistance increases with the decrease in electrode length. Why is that the case? So this, I would say, is a level 1 2 understanding. Plug and chug, give me the formula. I'll take a look at it, massage it, and give you the answer. Without looking around, what is the context in which the question is placed and what's being asked, and if there are any type of gray areas, nuances that we have to be aware of. Okay. The formula that this person is using, the student is using, applies to resistance of a wire, of a conductor in isolation. Correct, guys? I mean, we saw this formula in FE electrical. But we know that when we are talking about ground resistance, first of all, there's no straightforward formula. You've seen like Short's equation and this and that, right? They're all very complicated estimations, basically, right? Things are very different when we're dealing with ground resistance. And we know that when we increase the length of the electrode, the resistance, and I actually included this in the live training, is actually reducing. Why is that? Anyone? By increasing the length of the electrode, exactly, you're making more contact with the soil, right? With the ground. And that gives you more ability to actually, if there's a fault current, the fault current can then be dissipated. Okay, that's the reason. Okay, and the other reason is typically the deeper you dig in the ground, what happens? Anyone from Florida, South Florida? Anyone? I think in Louisiana as well, it would probably be the same case. If you dig deeper, what happens? What happens to the water table? Swamps, right? You actually get more and more contact into the moist soil, correct? And soil resistivity is going to go down. So increasing the length of the electrode in the context of ground resistance actually cannot be explained simply by this equation. There are a lot of other factors at play. And understanding these factors conceptually, theoretically, and relating them to actual practice, I think it's a fair game on the exam, even though they have not mentioned them in the reference handbook. Does it make sense, guys? Okay. So it was a good question. And I think that although it was seemed like a very basic question, I think it gives us good talking points, right? Okay. Another question I received regarding ground resistance testing was that Wasim, I had a question for you regarding this. He's referencing practice problem number 3 in grounding resistance testing, part 2 video. So guys, I would really appreciate if you can actually stick to the format, the guideline. So, some students are including the references within the body of the email, which is fine. But my preference is that, if I was to rephrase this question, the subject of this email would be um, PE power, because I'm running PE and FE programs simultaneously. Okay, so PE power, week number 1. Okay, general power engineering or measurement instrumentation, general power engineering, or section number 1, right? And then you're going to mention ground resistance testing, ground resistance testing. And then this is lecture example number 3. Okay. If you can stick with this format, I've included, I've explained this in the kickoff meeting as well. In every weekly office hours, you're going to see this format explained. So please, if you can stick with that, that would be great. Anyways, so his question is that uh, why couldn't I use the approximate formula, right? You gave me a certain value of A, which is, larger than the value of 2B. But exactly how much higher B would, how much higher than B would A need to be in order to use this equation? And here's my response. I recommend students to use the full formula, right, whenever they provided all the parameters. So in the question, or the way that I solved that problem, I actually had A at a higher value than 2B. I don't know what it was, like 2 times higher, 5 times larger, or 10 times larger. I had another student follow up later on, and then he came with some reference. It was not a very strong reference, so I'm not quoting that reference. But I think he said that when A is greater, larger than 2 times, right, and that factor has to be a 10. But my recommendation is that if you are given all the parameters that you need in order to use the full formula, just go with the full formula. Okay. Don't use approximate formula, because then you may actually miss out on the accuracy of your answer. Is that clear, guys? And that is a general position that I have when it comes to any of the approximate formulas. Okay. Ground resistance testing. So a very, very small question, 1-line question and a 1-paragraph, actually multi-paragraph answer. So let's work through this one. Okay. And the question starts out random thought. Okay. Would increasing the size of copper grounding conductor copper grounding conductor, not the electrode. So he's being very specific. So, you have the copper grounding conductor, right? The grid that is formed, okay? So he wants to increase the size. So let's say if we are using a 4-odd bare copper conductor, let's say he wants to increase it 250 kc mil, correct? Something like this. So he wants to increase the size of the conductor, decrease ground resistance more so than increasing the electrode diameter. Okay. So that's scenario A. Let's call it scenario A, where you're going from a 4-odd copper cable, grounding cable, to a 250 kc mil. And let's cook up a scenario B according to this, where you have, let's say, 1-inch diameter, 1 inch, and let's say you're going to a 2-inch, same length grounding electrode. Okay. So again, it's a very open-ended question, and the answer is also kind of open-ended. The answer to this question is that both of these, right? So actually, if you look at factors impacting the ground resistance, right, you have the increase in diameter. So you see, if you increase the diameter, your resistance does go down. Okay. Okay. So it does impact, and so does the size of the copper. Because if we use tiny copper wires, then the resistance of those tiny copper wires, R is equal to rho L over A, right, is going to be high, and that will basically impact the overall grounding resistance regardless, right? So the way that I answered this question is that both elements play a crucial role in creating low resistance. So if you talk about the grounding conductor, increasing the size of the cross section of the grounding conductor will reduce its resistance, right? This can lead to faster operation protected devices. However, this reduction may not significantly impact the overall grounding resistance when the electrode's resistance to the earth is much higher. So if it is already maxed out, or if you're already operating at limits, any incremental increase is not going to significantly impact the overall grounding resistance. And same thing can be said for grounding electrodes. Increasing the diameter of the electrode will increase its surface area in contact, leading to a decrease in the electrode's resistance to earth. However, the relationship isn't necessarily linear, and that's evident in here as well. It's not a linear, right? Because otherwise it would basically go something like this. At certain point, it's going to plateau, right? So in reality, right, if the grounding system already has a significantly sized grounding conductor, typically we don't go beyond 4-odd. It's very expensive. Copper is expensive, right? And you are just burying it in the ground. It is not being actively used. It only comes into play essentially when you have a fault condition or as a reference for your single phase systems, right? So you want to save cost on something that is buried in the ground. Or it may be used for lightning protection, but you guys get the idea, right? So if it is already appropriately sized, 4-odd is very typical, then the issue may likely lie with the grounding electrode, right? In that case, increasing the length of the grounding electrode and the diameter of grounding electrode will probably give you bigger bang for the buck. Why? Because grounding electrodes are actually spread more, there are few of them as compared to the conductor. So in terms of cost standpoint, it's a little bit cheaper. Okay. And if on the other hand, you already have maxed out on the length of the grounding electrode and the diameter of the grounding electrode, then maybe the bottleneck is your conductor. So it's not a straightforward answer, but I liked how the student was trying to compare and contrast and looking at it as an optimization problem. So Ricardo has a comment over here. Depends, but the length of electrodes is more effective than sizing up diameter of the electrodes and conductor. 100% agreed, right? So now Ricardo is taking another angle. So we are talking about the size of the copper conductor, right? And then the diameter of the electrode. What he's introducing is now the length of the electrode, right? And I 100% agree. I don't know if, I think I might have commented on this. Yeah, so ground electrode depth, right? So this has a huge impact because again, if in the first 5 feet, right, if you're digging, it's just soil, dirt, dry sand or whatever, right? But as soon as you go past, let's say hypothetically 10 feet, okay, let's say 3-meter electrodes are actually not that uncommon. 10 feet, right? 9 feet, 10 feet. And then you hit water table, right? You hit water table, then that is going to immensely increase the effectiveness of your grounding grid and reduce the ground resistance. Does it make sense, guys? Okay, so good open-ended theoretical application-based question. If you like this video, then please don't forget to subscribe to this channel. Feel free to ask me any questions in the comment section of this video below. You can find tons of success stories of my FE Electrical and PE Power students over here. And if you want to learn more about preparation of FE Electrical and Computer exam and the PE Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.